Okay, so we are on chapter 8. This is proofs involving sets, right? We did sets way back at the beginning of the course. You're starting to forget what all that means. Well, they come back. All right, so let's use sets. So the most common proof with sets you're going to need is proving that you have a subset. What was the definition for A to be a subset of B? Yeah, every element of A is in B. So here's how you would do a direct proof. Okay, so direct proof. You're going to let, whatever you want to call it, X be an element of A and show X is an element of B. Right, yep, that's it. Because this X is arbitrary. So what you said is I take a random element of A, it could be any element of A, I always then can follow this logic to show it has to be in B. That means everything in A is in B. Okay, so that's it. So let's look at an example. All right, so here I have the set of all natural numbers that are a multiple of 8, and I'm saying that's a subset of the set of all natural numbers that are a multiple of 2. Everybody see that? 8 divides X means X is a multiple of 8. 2 divides X means X is a multiple of 2. So first of all, does that make sense that the multiples of 8 are a subset of the multiples of 2? Yeah, because 16 would be both, but like 12 would be a multiple of 2, but not 8. So makes sense. So let's see how our proof will look. So proof. So that I don't have to write what these sets are over and over, I'm going to give them names. So let's let A equal the set of all X in the natural numbers such that 8 divides X. And B equal the set of all X in the natural numbers such that 2 divides X. And again, this is just to save me space because I just don't want to have to write that set over and over and over. Now I can just write A. Okay. So now we are going to show our subset. So I'm going to let little a be an element of capital A. What is the qualification to be in set capital A? Have to be a multiple of 8. So we'll say then 8 divides little a. So there exists k in the integers with a equal to 8k. My goal is to show that that's in set B. Well, what type of numbers are in set B? Even multiples of 2. So I'm going to say, but A equals 8k equals 2 times 4k, right? So I've shown, yes, A is a multiple of 2. And 4k is an element of the integers. So little a is an element of capital B. And if you want, for when you look back, you could say, so little a is an element of B since 2 divides A, but it's up to you if you want to say that. Therefore, capital A is a subset of capital B. So the setup here isn't too bad. You take something from the one you want to be the subset and show what's in the one you want to be the bigger. Well, bigger, they might be equal, right? But bigger one. It's just those details in the middle completely depend on what sets you're looking at, right? As to what could happen and how complicated it could get, okay? So any questions on that one? Now, technically, when I make this statement, I'm technically ignoring one possible situation for capital A. The empty set. Think, well, crap, what if A is the empty set? Then I can't pull an element out of it. But what did we say about the empty set in terms of subsets? The empty set is always a subset. So some proofs will actually, some proofs will actually add in a line at the beginning that would say if A equals the empty set, then A is a subset of B. And then they would say, if not, blah, 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 blah. Okay. That is a little over meticulous to do that. But sometimes that'll end up being important to think about. But in general, the empty set's a subset of everything. So yeah, if it's the empty set, it works. Move on. Okay, so we often don't even write it in, but just be careful about that. All right. So now that we talked about subsets, we can talk about equals. Does anyone remember what we said it means for two sets to be equal? They have the same elements. Yeah. How can I describe that in terms of subsets? Yep, A is a subset of B and B is a subset of A. So basically, I'm going to show an element of A has to be in B, and then show an element of B has to be in A. Therefore, they have the same elements. It's kind of like our if and only if proof where I'm going both directions. Okay. All right. So let's look at an example like that. So here I have my sets. I'm going to give them names. What is that first set describing? Multiples of 6. So why don't we call it capital S for 6? What's the next set describing? Multiples of 2. I'm going to call it E for even. And the last set? Multiples of 3. So I'll call it T for 3. Set. I didn't even notice that. That's funny. No, I swear I didn't. I'm not that clever. Okay. So proof. I did make up the notes myself. You're right. I should be that clever. I will. Okay. So we are going to say let S equal the set 6n such that n is an integer. E equal the set 2n such that n is an integer. And T equal the set 3n such that n is an integer. Okay, so that's my assumption. Now, I need to show subset both directions. So I'm going to start with S, show it's an E intersect T first. So let's let X be an element of capital S. Well, what's that mean about X? It's a multiple of 6. Then there exists, we'll do M in the integers with X equal to 6M. All right. I want to show that that's an E and T, right? It needs to be in the intersection, so it needs to be in both. What's it take to be an E? Has to be even, it has to be a multiple of 2. So say note x equals 2 times 3m. What's it take to be in T? Multiple of 3. So I can rewrite that to 3 times 2m. Okay. So the first arrangement shows x is an element of E, and the second shows x an element of T. Thus, x is an element of E, and x is an element of T, meaning x is an element of E intersect T. Ergo, S is a subset of E intersect T. So that was the easier direction. The next direction is not going to be hard, but it'll take a little thinking. Okay, so for the next direction, I want to do a little scratch work for us to think about. In the next direction, I'm going to assume x is in E intersect T. So that's going to mean x is 2k and x is also 3L. And what's my goal to get x in what? I need to get x in the form of 6 times something. So you see why this one's not quite as obvious. It's going to have an extra step. All right. Well, tell me something. If x is 2 times k, what type of integer is it? It's even. But he's also 3L. What does that tell me about L if 3L equals an even number? L has to be even because 3 is odd. So if L were odd, I'd still stay odd, right? So that's where we're going to get our 6 from, is L has to be even, okay? So let's go back to our proof. All right. Let x be an element of E intersect T, then there exists K, L in the integers with x equal to 2k and x equal to 3L. Since x equals 2k, x is even, meaning 3L is even. But this is only possible if L is even. So there exist, what haven't we used? Let's use J. There exists J in the integers with L equal to 2J. Thus, x equals 6J, which means x is an element of S. Thus, E intersect T is a subset of S. Therefore, S equals E intersect T. Done. All right. Any questions on that one? Yeah.
Go back to the screenshot.
Yes. There you go. Who knew you'd have to write so much in a math class, huh?
Every day I walk in here, then my someone there, is it gonna be that long one that you say you do?
No, that one will come. So the long proof will come chapter 10 material, I think.
But that's extra close now.
Yeah, that is close. It's either 10 or 11, but yeah.
How many
I think we're only going to do 12 or so, but 10 is a long chapter. 10 is a long chapter. So basically, I gave you a preview of coming attractions. The next big proof technique and the last big one is called induction. It gets a little algebra heavy. It's a very useful and very good technique, but it'll take us a little while to work on that one. So, yep. All right, so 8 and 9 are a little breather, kind of. Okay, so here we go. Let's do another one that's an equals. So I got to do a subset both ways. All right. Do proof. Notice this one, I'm not told what A, B, and C are. They're just sets. I don't know what type of things are in the sets. It doesn't matter. Okay, so we're just going to start. Let A, B, and C be sets. All right. So I have a Cartesian product. What do the elements of Cartesian products look like? Ordered pairs. So we're going to let X comma Y be an element of A cross B union C. But by definition of Cartesian product, right, that means X is in A and Y is in B union C. So then X is in A and Y is in B union C. That's how Cartesian products work. But let's use that definition of union. What does the definition of union tell me about Y? So Y is in B or Y is in C. If Y is in B, X comma Y is in A cross B. If Y is in C, X comma Y is in A cross C. All right. In either case, X comma Y is in A cross B union A cross C, right? Because either it's an A cross B or it's an A cross C.
I'm gonna do with this Is it okay if we just write them in different colors so we know what we're doing? I feel like
Yeah.
if I'm writing in black, I'm like, it's
Yeah. No, for me, I'm fine if you use colors to, keep track of different parts. That's fine. Especially if you're writing on a tablet where it's easy to switch colors or something. Yeah, that's fine. I will tell you though, when you're reading your textbooks in your future math classes, right, it'll be all in black. They're not going to color code it for you. Okay. They're not going to be like, this direction's red, this direction's purple. No, all black.
But they
You can color
highlighters.
code it yourself. That's right.
They make highlighters and pens and different types of.
Yep, abs, and that's not a bad idea. To when you see a proof in a textbook, I'm just writing the subset part now. When you see a proof in a textbook, to go in and color code different parts of it to follow the structure of the proof, that's actually really good practice. Okay, so, all right. So we took something in A cross B union C, showed that it has to be an A cross B union A cross C. All right. So now the other direction. Let XY be in A cross B union A cross C. Well, definition of union, it had to come from one of them. Then XY is in A cross B, or XY is in A cross C. In both cases, X is in A, right? Whether it's an A cross B or A cross C, that X came from A. In both cases, X came from A. Okay. Let's say, see. For the first, Y is in B, and for the second, Y is in C. Thus, Y is in B, or Y is in C, meaning Y is in B union C. So just got to write our conclusion stuff here. So X is in A, Y is in B union C. Thus, XY is in A cross B union C. So A cross B union A cross C subset A cross B union C, meaning the sets are equal. I ran out of space, so we'll write that in words, meaning the sets are equal. All right, so first of all, any questions on the logic of the proof? Okay, now second, notice that it was pretty much the exact same logic backwards the second time, right? That first proof we did, the logic was different between the two directions, okay? But this proof, it was pretty much the exact same logic backwards. When that happens, we can actually, there's a shorter way to write it. Well, not going to be shorter space-wise, but shorter wordiness-wise, okay? So let me show you how we can condense that. So if you look at the next page, it's the exact same thing because we are going to rewrite this proof in a short way.
Oh, that was the long way?
Well, that was the wordy way. Let A, B, and C be sets. Then all right, here we go. So I'm going to do a series of if and only if statements kind of in columns like I would an equation. So this will be my left side. We're going to say X is an element of A cross B union C. If and only if, so put your arrow, your double arrow. All right. X is in A and, oh, I should have put XY, shouldn't I? I'm sorry, guys. Shame on me. Okay. XY is in A cross B union C. So then X is in A and Y is in B union C. But what does it mean to be in the union? You're in one or the other. So X is in A and parentheses, Y is in B or Y is in C. If and only if, but that's the same thing as X is in A and Y is in B, or X is in A and Y is in C. Okay, notice that step going from the and with the or inside, the and or and, that was one of our logical properties we were allowed, okay? All right, so I can now interpret if X is in A and Y is in B, that means XY is in A cross B, or X is in A and Y is in C, so XY is in A cross C. And now we get to what we want. XY is in A cross B union A cross C. Now we still have to write our closing sentence, but we have all our logic of our proof right here. Whenever you write one like this, you need to be 100% sure your steps reverse, because we wrote it starting here and then worked our way down. So we followed the logic that way. You need to double check the logic works backwards. So if I start in the union, yes, I get an or, then yes, that's just the definition of cross product. Then yes, that's a logical rule. I'm allowed to do that, right? Making sure it traces backwards. If it doesn't trace backwards, that means you need to write the two separate subset ones, okay? But if the logic's the same for both, this is way easier. We took the same amount of space, but it was way easier, right? To write out. Okay, so then we could say, thus A cross B union C equals A cross B union A cross C. You do not have to use one specific type if either way will work. Okay, this is just kind of a shorthand way. If it fits, you can do the shorthand way if you want. Any questions on that? Okay, example 4. So here we have the following are equivalent. In fact, an abbreviation for that, sometimes you'll see the following are equivalent. Some mathematicians, because again, mathematicians like to use it the least amount of writing as possible, believe it or not. They'll put TFAE. Okay, if you ever see that in a book, the following are equivalent. Kind of like your WLOG, meaning without loss of generality. Okay. Yep. All right. So I have 3 statements here. I want to show they're all equivalent. So I'm going to go about this by doing statement 1, and then I'll use that to show statement 2. So I'll assume 1 is true, show that that gives me 2. Then I'll assume 2 is true, show that gives me 3. Then I'll assume 3 is true and show that gives me 1. So that's going to be my approach. So my proof is going to have 3 separate proofs in it. I can do them in whatever order I want. Typically, unless you're putting it off because it's going to be a pain, you start with the smallest. All right, so we are going to let A and B be sets with universe U. All right. Remember that universe, that universal set is everything I'm considering, right? So that's everything that's allowed. All right. So let's notate what we're doing. So we're going to do 1 implies 2. Sometimes people notate it, sometimes they don't. For our purposes, it'd be good to help keep track of what the heck we're doing. All right. So that means I need to assume 1. So I'm going to assume A is a subset of B. All right. All right. I want to show.
Oh, 1, 2. I'm sorry.
Yeah, 1, 2. Okay. I want to show A intersect B complement is empty, right? That's what I want to show. I want to show 2. I want to show A intersect B complement is empty. Everybody see that? Well, oftentimes the easiest way to show something is empty is contradiction. Say, well, what if it's not? What if something was actually in that intersection? Why can't that happen? So for contradiction, assume there exists X in A intersect B complement. All right. If it's in the intersection, it has to be in both, right? So then X is an element of A and X is an element of B complement. Well, what was my very first assumption for this part? A is a subset of B. So if X is in A, what's that mean? X has to be in B. That's what it means to be a subset. But X in A means X is an element of B, since A is a subset of B. All right, we can be super explicit here. Thus, X is an element of B and X is an element of B complement. Well, that's definitely an impossible situation, right? How can it be in a set and the set's complement? That's not possible. Those are complete opposites. So that's our contradiction. So I'm just going to put lightning bolt. You could say this is a contradiction. This is impossible. Thus,
Most of our teachers know this.
it's a good question. I think most of the professors here know lightning bolt. That means you can always ask, you know, say, can I use lightning bolt for contradiction? That's fine. I know the other Dr. Gamble. My husband knows, but yeah. All right. Yeah. Okay. So thus A intersect B complement must be empty. Right? Because if something was in it, we get the impossible situation. So nothing can be in it. All right. That was our first one. 2 more to go. 2 implies 3. So now we're starting over, right? Everything we said in that first part doesn't matter. Wiping the slate clean and assume A intersect B complement equals the empty set. So that's what I'm starting with. That's what I'm assuming. Now I need to show that B union A complement is the entire universe that I'm considering, is all possible elements. Okay. So 4 equals the universe. I guess I should technically show subset both ways, but one's kind of stupid. So we can say, obviously, if I could spell right, obviously, B union A complement is a subset of U because it's the universe. Everything's a subset of it. It's all possible things I'm allowed to consider. Okay. All right. So we only need to show the universe is a subset of B union A complement.
I'm just wondering.
Mhm.
Why would you want that?
What's my goal here?
Those are very equivalent.
To show they're equal. So I need technically to get subset both ways. It's just that one way was stupid. So I just stated, duh. Okay. Yep. Oh yeah. Well, how do we show subset? We let X be an element of U. So I take a random element from the universe. It could be I'm looking at natural numbers only, so it's a random natural number. Could be looking at real numbers. It's a random real number. Okay. So a union means it has to be in one or the other, right? So we're going to do 2 cases. Either it's MB, is that the way I want to do it? Or it's not MB. Yeah, let's do it that way. So if X is an element of B, then X is an element of B union A complement. If X is not an element of B, all right. Well, if X is not an element of B, it has to be in B complement, right? Then X is in B complement. Now look at my initial assumption for this part. What did I assume for this part? A and B complement have nothing in common. Yeah, their intersection's empty. So if X is in B complement, what do I know for a fact? It's not an A, okay? So X is not in A since A intersect B complement equals the empty set. This means X is an element of A complement, implying X is an element of B union A complement. Either way, X is an element of B union A complement. I guess we can write conclusion here. So universe is a subset of B union A complement. So that's that direction. All right. One more to go, and then we'll have the following our equivalent proof. What do I need to assume to show 3 implies 1?
What do you do? Assume that B union
Yeah, B union A complement equals the universe.
A.
Yep. No, you're good. Now what's my goal? A is a subset of B. So I'd better start with let X be an element of A. And I want to get to the fact that X is an element of B. Well, if X is an A, it's definitely something from my universe because that's all my elements. Okay. And what do I know for sure about X and A complement? It's not an A complement. So this is actually a pretty short little proof here because the universe equals B union A complement and X can't be an A complement. It has to be in B. So that's our logic here. Let's write it out. So X is an element of B union A complement since B union A complement equals U equals the universe. This means X is in B or X is in A complement. But X cannot be in A complement since X is in A. So X must be in B. Thus, A is a subset of B. There we go. We proved those 3 statements are all equivalent. Any questions on that proof or proofs with sets in general? The key when you're dealing with proofs with sets, right, is just remembering what things like union and intersection and complement and all those mean. Because oftentimes you notice our proofs, especially at this level, just go back to using that definition. Union means it's in one or the other, right? And just taking that and working with it. So, yeah. All right. That's chapter 8.